Never. Never. I already don't do what I want to do as much. What do I want to do? I want to write programs and write papers. I want to do what the graduate students do, right? That's fun. I don't want to advise people. Sorry. Sorry, those of you who I advise. But it dawned on me one day. It's like, you're doing what I want to do. I like writing code. I like doing JGraph, right? I like doing that. Do I like writing grant proposals? Oh my God, no. It's terrible. Why on earth would I be a department head? I mean, really. Yeah. I mean, I'd have to wear good clothes, get up in the morning, grind my nose up the administrators' asses every day, right?
Probably for shoes, right?
Yeah, all of the above. I don't think they'd take me. That'd be very interesting. Plus, I also don't think our department can have a computer scientist. I actually think the engineers refuse to allow computer science. Every head we've had since we've merged has been EE or CE. Right, and I think Rose will be it. I mean, I think Rose is going to be our next department head. I don't want him to be, not because I don't like him. I love Garrett. I want him doing research with me. I don't want him wasting his time being a department head. I've told him this, right? But I think he wants to do it. So, and he'll be great. He'll be great. I don't know what'll happen to our research. Anyone work for Dr. Rose here? No, okay. He might not want to. All right, y'all enjoying all this political talk? Let's talk about a B tree. We have how many minutes left now? 15, 17? All right. Do I not have an index.html? I don't. That's interesting. Okay. There is a resource. Let me find it. It's probably linked off the lab. I do have a new machine. They're setting it up. Lab staff. I might hit this one with a bat. I really might. When I get the new machine, I might not even keep this one around. I might just sledgehammer it.
Can you record it?
What's that?
Can you record it?
If I do, I will. I probably won't. I did it for my neighbor though. He was like, I tried to use his computer because I wanted to use it for my snake room cluster, but it was too slow. And I was like, "Do you want me to just get rid of it?" He's like, "Yeah, but can you wipe the hard drive?" And I'm like, "Sure." I just beat it with a sledgehammer. There you go.
Did you add that one to the sneaker?
Was that?
Did you add that one to the sneaker?
No, you know what? I got to figure out power because this one, if I run it, if I burn the CPU on this one all night, the battery runs out. So I don't understand the power of this one. So I got to figure that. And I just told you, I don't know what power is.
You do the good old leave it plugged up.
Well, I did. No, even when it's plugged in, it runs out of battery. So I don't know. This is the worst computer ever. Okay.
What did you get for a new one?
What's that?
Which one was the new one?
I don't know. It's the latest Mac. I mean, they're no good computers except for the Raspberry Pi 5, but I can't use that as my main computer. I mean, as much as I'd like to, I can't.
That was so fun.
All right. I give you on the lab write-up. I give you this is a really nice website on B-trees. So that's your reference material. There is a little difference. I tell you about the difference in all of these. Okay, the whole point of a B-tree is, okay, so a B-tree is a multi-way tree, not binary. And there's a very specific reason why. The reason why is a B-tree is meant to be a disk storage system. Now, disks have very important properties that differ from your regular CPU usage, right? So when you use a map, you're using a red-black tree, which is a binary tree, which makes sense. With a disk system, the problem with the disk system is that my main overhead is reading a sector, right? Reading a sector takes like a millisecond. Now on an SSD, it's faster, but not that much faster, and certainly not fast compared to the 2+ gigahertz my CPU is running at. So the thing about when you're dealing with a disk system is reading your sector takes all the time. If you run through your sector linearly, that's fine. That is in the noise. Okay? So you have to twist your thinking because now a binary tree doesn't make sense. Because if every node were a disk sector, now you're reading too many disk sectors because your tree has some depth to it. So what the B tree does is a B tree packs a bunch of stuff into a single node, and the whole idea is a node's going to fit exactly on a disk sector, And now your goal is to minimize the disk sectors that you read. Okay? So that's the whole point behind a B tree. Now let me grab my OpenOffice and get rid of that first page. Okay, now we're going to start with a multi-way tree. So we have a multi-way tree, which is the heart of a B tree. Now with your multi-way tree, you are going, I hate the word order. You're going to store keys, and then the way this works with us is you're going to store keys and you're going to store disk sector pointers. Those are your vals in your tree, okay? So each one of these nodes is a disk sector, and that's why I kind of draw them all as storing the same thing. They're going to store some maximum number of keys. In this picture it would be 4, and then you're going to have that plus 1 links to other nodes. And now these links are actually going to be sector IDs, logical block addresses, because a node is a sector. So in this example, my disk sector is going to hold 4 keys, 5 vals, right? And then the way you do search to find something in this, like if I want to find R, I'm going to read the root, I read the whole sector, I'm going to run through it linear and find out where would R be. Well, it would be after P. It's not there. Since it's after P, I've got a pointer to a block after P. I chase that pointer, I read the next block. And then I say, where's R? Well, it's between Q and T, so now I'm going to find this pointer, go there, and that's where I find, and now I've found R. Okay. So that's an example of a multi-way tree on disk. This is not a B tree. This is just a multi-way tree that's on disk. Okay. Now, what makes a B tree? Oh, I must have made a copy. All right. Have at least. That is a very important word that I've kept out. Yeah, Brian.
So just like a high level, is this like eliminating the need for like a fat and just reorganizing the disk?
Yeah, no more fat. No more fat. This is a completely different way of storing. And B trees are usually like database kind of things. So they're not really, you don't build a file system. Like fats, you build a file system from. B trees are usually at the heart of like giant database systems. Okay, so it is going to be a different model. It's on disk, but it's not a file system like we did with the file allocation table. Okay, the invariance, we have fixed the order. The order is 1 plus the number of maximum keys. Why am I using this? Because the dude did it in the website. And this is the standard definition. Okay? Every node in your B tree, okay, has at least, basically, m over 2 minus 1. If my order is 5, every node has to have at least 2 keys, except for the root node. Okay? It can have up to m minus 1. Right? But it has to have at least that many keys. And then all your external nodes in your tree are at the same level. This is an important thing, and this is what gives you the balance condition. I'm not going to preview jack about the balance condition. B trees are super balanced, especially practical installations of them. So, oh, there's the at least, right? So this is not a B tree. Why? Because that node has too few keys in it. The root node can have any number, but the internal nodes have to have at least that many keys. And all the nodes aren't at the same level. All the external nodes aren't at the same level. We have 2 at 3 and 2 at 2. That can't happen. In a B tree, they're all on the same level. Yeah.
Are the externals the same as leaf nodes?
Yeah. 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 And there's kind of well, I'll get to it. There's an interesting thing about practical installations of this, but we'll get to it. Okay. Now, what we're going to do is we're going to build a B tree. And this example follows that web link I gave you for the website from St. Vincent's. I do the same examples as he does. Okay, so first thing you do is it's just like Eric's try. How do you do search? You look for it. How do you insert? You look for it, and where it's not there, put it where it should have been. Okay, so if we're going to insert C, G, and N, we're going to insert C here, and we're going to insert G there, and then we're going to insert N there. Keep them in order. Okay, that's a B tree. Right. We'll talk about data in a little bit. I'm just talking about the keys at this point. Okay, so now if I want to insert A into the tree, right, B trees, again, you kind of think, well, this is inefficient. Doesn't matter. The inefficiency is reading this from disk. When I want to insert A, what am I going to do? I'm going to move N over, I'm going to move G over, I'm going to move C over, and I'm going to put A where it belongs. And yes, that seems inefficient, but it's in the noise because my processor's coming along at 2 gigahertz, and reading that sector took me a millisecond. Okay. All right. Now, I never took attendance. The downside of knowing everyone's name. Or it's a good side. There we go. You don't have to smile. You don't have to smile. You know, you can smile. Back. There you go. They're smiling. That's good. You smiling. Good job. You smiling. And don't think I didn't notice, Will, that you were doing this last time in the picture.
I don't think it was quite like that.
Okay. All right. Now, suppose we want to insert H. Now, I'm going to beat this one into y'all's heads, okay, because this is going to help you with your implementation. The way this works. So now, your node is stored on disk, and then you're going to read it into memory. Okay. Now, what you're going to do when you need to insert something, there's not room for it, right? You're going to allocate room for it. Okay. And then you're going to act like the node is big enough. So here's H. It's there. It's in memory. This isn't on disk yet. Okay? It's in memory. And now you see it's too big. So now what you're going to do is you're going to split it out. You're going to say, all right, I need a new node. How do I do this? Here, I'll copy paste. I'm going to have a new node. I'll allocate a new node. And then I'm going to move H and N over here. I guess I need 2 empty keys. Sure. There we go. There are my empty keys. Okay. I'm going to do that. I'm going to get rid of that because it's. And then I'm going to keep the A and the C, but now I'm going to go ahead and delete this because it doesn't get stored on disk. All right. I'm going to get rid of these keys. Right, so they're gone, and now, and then what I'm going to do is I'm going to take that middle node and kick it up to my parent. And if I don't have a parent, I'll create a new root. So that's what happens here is I'm going to create a new root whose value is G. That's there, and then we're going to have pointers. All right, that's going to point to that, and that's going to point to that. Right. Yeah, Lexi.
How does it decide which ones to keep down and which ones to keep up? And since you said 7, does the order have to be odd?
It doesn't have to be odd. You just have to be consistent about what you do. But if the order's odd, it's a lot more convenient because if the order's odd, this is where you get n over 2 of them minus 1 go into the left, n over 2 of them and the minus 1 go in the right, and we kick the middle one up to the parent. And then if it is an even number, you do what I do. You'll be probing my code so much that'll just be in the noise. Okay, so let me see if I've got that. Oh, there we go. Or did I just create that? I just created that. All right, yeah. All right, so now let's keep going. All right, so now if we insert, every time we insert, it goes into a leaf node. Okay, so we don't ever insert into the internal nodes, just to the external nodes. So if I do E is going to be here. K will be here. We'll move the N over. All right, and then Q goes here. So I'm all good. That goes into the leaf nodes. Then I insert M. This is going to require a split. Now, if I'm not mistaken, do I draw the picture nicely? I do. So let's just look at the picture. So again, I insert M. I pretend my node's too big, and again, in memory, what you're going to do is you're actually going to allocate room for an extra key and an extra val, even though it's not on disk, and that helps you split. But then when you write to disk, then you go ahead and coalesce it and write it into a disk sector. That single, I can tell you, that single design decision saved me a week of work. So. Okay, so now what's going to happen is, here's the picture, right? It's too big, so now what I'm going to do is these keys stay, these keys are going to go into their new node, and N gets kicked up into the parent. Yeah?
Can you reiterate what you just said about that some of the values?
Oh, yes. This is my design decision. So again, this like fits exactly in a disk sector. Okay? There's no extra room here whatsoever. But when I allocate memory for it, I'm actually going to allocate room for an extra key and an extra val in memory. Okay? And actually the way this works is the way this works on disk in your lab is the first byte says internal or external node when you're reading your sector. The next byte tells you the number of keys that are actually in the node. So 3 here, 1 here. Okay? Then there are a whole bunch of bytes for keys because your keys can be up to like 250. Your key size actually is fixed on your disk, but it can be as big as 250. Okay? So then all your keys go there, and then at the end of the block is where I have your logical block addresses here. Okay? So when you read this from disk, you're going to read this from disk, you're going to allocate a data structure that actually has room. You're going to allocate these guys separately in their own data structure. You'll allocate extra room so you can keep an extra key. And that way it's easier to split. It's so much easier to split when you do that. And then when you're done, basically you're going to take your extra logical block addresses, mem copy them where they should go in the disk sector, and flush the disk sector. What's more fun than that? But I said that decision, what it means is that whenever I split, I know I have a node that looks just like this. Regardless of where it went in, regardless if I'm sort of the first one or the last one. When I split, I know I've got that so I can write a split routine. And it makes life so much easier. Yeah. I've written this lab twice. The first time I didn't do that.
So
Yeah.
at the beginning, do you already allocate enough space for the extra?
Yeah.
Okay.
Yeah, when I read a block from disk, I actually allocate an extra array for my logical block addresses. I read the sector, I mem copy the logical block addresses from the sector from that memory into my new memory, and then I've allocated room for the extra keys.
So really, you just pretend that they're actually smaller the whole time?
Sure. We'll go over it. I'll go over the data structure. But anyway, this is all there is to a B tree. A B tree is easy. That's just it. You just split. It's big. You keep inserting. You keep splitting. Right. Eventually, the root fills up, and once it fills up, you got to split it. That's how you get a new level of your tree. Is the root fills up, and you have to split it and pop a new thing up into the parent. Okay. I have slides on deletion. We don't implement deletion. That would be an extra 3 weeks. So we're not going to implement deletion in our B trees, but that's just insertion. Okay, time's up. That's good. I'll see you Tuesday.